Thank you for the introduction. I would also like to thank the organizer for granting me the chance to talk about my PhD project. I'm gonna talk to you guys about what we did in the last year and a half, more or less, which is to build a new setup to measure collective light matter interaction. So my presentation is structured as follows. I'm just gonna give a bit of context to what I mean by light matter interaction. Then I'm gonna talk about the building of the setup, how we do measurements, and the most recent results and what we would like to do next. So let's go. Okay, so matter for us is cold atoms. So cold atoms can effectively be prepared to behave like two-level systems. We have an excited state, a ground state, separated by an energy h bar omega 0. When the system is in the excited state, it will naturally decay with a time constant gamma, which is given by the excited state line width back to the ground state. So the interaction of such system or of an ensemble of independent systems like this one is well understood. It's what we call the optical block equation, which most of you, I guess, are familiar with. And if we plot them for the population of the excited state, we'll get, when undergoing a resonant driving above saturation, we will get a first dynamical part, which are the Rabi oscillation, that will then decay to a steady state. And when we switch off the drive, we will go back to the ground state with the same decay constant. Cool. Okay, so what makes it interesting is to try to see when ensemble of these systems actually interact collectively with the light modes. There are several ways to do this. Just to mention some groups do put the ensemble of cold atoms into cavities that will then lead to a collective coupling of these atoms to the cavity mode, or they trap these atoms near nanofibers, as somebody already presented during this conference. I am here to talk to you about another approach, which is completely in free space. So the idea here is that we can trap many atoms, like up to several thousands of atoms, in a very dense cloud. So this cloud, as you can see, has an elongated shape. One of the dimensions is way bigger than the other. And the small dimension is comparable or smaller to the transition wavelength, which is also given by just the two-level system physics. What happens if we do that? When they are in such a situation, the atoms will interact with each other via mostly dipole potentials, and the shape and this dipolar interaction will lead the atoms to couple collectively to the light, will lead the atoms to populate collective states, and when decaying or when interacting with the light in these states, the emission light will be modified. I don't have the time to go into details about this process, but basically I just would like to mention two phenomena. One is called superradiance and the other one is called subradiance. They are called this way because for superradiance states, the decay process is much faster than the natural line width of the atoms, and for the subradiance, it's the opposite. It's a bit slower. So this is the general framework. Now I'm going to describe it very quickly, the setup. So this is the core of our setup. It's the vacuum part. The atomic species that we use is rubidium, which is a standard species for cold atoms applications. There's a bunch of parts that help us to get a good vacuum, but the important part here is the atomic source in magenta, which is a two-dimensional magneto-optical trap. It's also like a commercial atomic source. And then the important part is, the important part is here is the science cell, which is a glass cell. In the science cells, we will load a three-dimensional magneto-optical trap from the atomic source. So here is where the science happens. But we do want to have dense clouds. So we do not work directly in the MOT. We work in what are, in jargon, called optical tweezers. Now, optical tweezers are tightly focused laser beams. Physically, we focus them via these microscope objectives that I put there with an NA of 0.5. The light beam must be red detuned with respect to the transition. So for rubidium, we are always in the near infrared. So the wavelength of the trap is bigger, 935 nanometers, with respect to the line of rubidium that we are going to use for physics. The waist is pretty small. Now we have a tunable setup, so the waist is going to go from 1.5 to 5 micron, more or less. Now, the challenge is to have several thousand of atoms in this optical tweezer. There's one caveat, which is when we load directly from the MOT, there's a known phenomenon, which is light-assisted collisions, which will, in fact, impact the loading on the trap and will reduce the number that we're able to load in this trap. So how do we get around that? We add a step. We add a cooling step. We exploit the fact, we take advantage of the fact that the rubidium has an alkali as a doubly degenerate ground state. And we use a different transition than the one, we use a different transition than the one that we use for physics. And we excite both transitions from both ground states. They each have a detuning. Here I indicated it as delta 1 and delta 2 that we're able to control independently. And the nice things that happen when this detuning coincide is that the two ground states will combine into a symmetric and antisymmetric state. They are called B and D because B stands for bright and D stands for dark. So the atoms will spend most of their times in the dark state, which is what we are aiming for, because then we will load them into the optical tweezer while they are in this dark state. Additionally, these procedures also cools them down a bit. It's similar to the Sisyphus cooling for those of you who know it. This effectively works. This is a measurement on our setup where you can see the peak is where the two detunings, delta 1 and delta 2 coincides, and that's where we have the peak of atomic number in the trap. So we got our dense cloud. There's a few steps to have a dense cloud of 2-level atoms because we just use some properties of the spectrum of rubidium, which is a multi-level atoms as all the atoms, basically. So what we do is that we select a cycling transition, which is the one from the ground state f equal 2 to f equal 3, from the level mf plus 2 to plus 3. We isolate this transition by applying a strong for our standards, magnetic fields. And additionally, what we do is we try to pump all the atoms in this mf plus 2 ground state so that we have most of them in this state and we can work in this 2-level system. So this is the framework. Now I'm going to show you what we measured recently and how we measure them first. So what we look at is just the light emitted from the atoms. So going back to the experiment, of course, the objectives have also the role of detecting the atomic fluorescence. So here I show you that we can shine a resonant light beam on the atoms to drive the dynamics. And from the two different objectives, it's nice that we have two because we can look at the same time to the space resolved fluorescence on a camera and to the time resolved fluorescence on an avalanche photodiode. Just to be clear, we are exciting the atoms with a probe which is perpendicular to the natural axis of the cloud, whereas we're looking at the fluorescence along the axis of the cloud. Our first step is to check that we actually prepared them correctly as a 2-level system, which we did. This is a measurements done with a dilute cloud. So when they are independent, it's nice, like they behave like 2-level systems. We see the Rabi oscillation that change if we increase the driving strength. And in this case, the intensity of the emitted light is just proportional to the population of the excited state. Now, if we do the same thing with a denser cloud, I'm going to show you now. Okay. What we see is that what happens is quite differently. So the intensity of the light will be affected by this atomic correlation due to dipolar forces that I mentioned. And as you can see here in the graph, the red dots do not lie on the dashed black line. The dashed black line is the optical block equation, so the independent emitters prediction, but they go above, especially in these first two oscillations. Now, this is known to be a signature of the phenomena of superradiance. To be a bit more convincing of that, I can also show you what happens if we, instead of looking just at the dynamics at the beginning of the driving pulse, but instead if we look at the final part. So this is when we switch off the driving and we just look how the system decays back to the ground state. It's not a super striking effect. These are very very, very new measurements. But what I want you to take home with you is that here the optical block equation are the dashed green line. And when our cloud is not dense, so when the atom number is low, the black dots are lying on this prediction. Whereas when the cloud is denser, the atom number is way higher, these red dots do show a faster decay, faster than exponential decay with the natural line width of rubidium, which is in fact the definition of superradiance that I just gave you at the beginning. So this is kind of nice. So we probed these collective effects that had already been measurements on the previous setup. So now what we want to do next is to go beyond these effects. So first, we would like also to add the radial detection. So there's a place on our setup for a third objective. This would allow us to detect the fluorescence perpendicular to the trap. This is interesting because the shape of the trap actually determines a different coupling to the light modes, whether it's axially or radially. And then the idea is to try to tailor this decay constant with a pulse scheme, with a pulse excitation scheme. This is to try to explore the other phenomena that we did not witness yet, which is subradiance. Another short-term idea is to measure time correlation function, in particular to see, to explore what happens during the steady state of the pulse. This is not too hard to do on our setup. We can easily measure 2 times correlation functions. And again, on the previous setup, we had already some interesting effects. And lastly, I'm concluding. So this is more a long-term project in collaboration with other laboratories, in particular the Castle Brosser laboratory in Paris. Try to see what happens if we send squeezed light onto the atoms and what comes out of it. And with that, I thank you for your attention.
Thank you very much. Any question? Oh, 2 of them over there.
Thank you for this talk. So first, on what order is the optical depth? You actually measure the optical depth?
We never measured it. I don't think it's very... really on the it's very thin radially the cloud, so it's below a wavelength. So I don't think it's.
Okay, and just a small question also. Do you can you model this same thing with the Beer-Lambert law, like just classical modeling rather than the optical Bloch equations, or you didn't try, or
like with the classical model of dipoles interactions, or so I don't know. It's
like
also
the coupled dipole model, for example.
with what? Sorry.
The coupled dipole model, or or
yeah,
random walk.
Yes, so it depends what you look at, but yes, you can have a coupled model interactions based models. So the thing is, so basically, sorry. So it depends what you look at, because like this part here with a coupled dipoles model, you would just assume that these correlations, you can rewrite it like 2 independent things, that this is equal to the 2 independent quantities. So some of the things, you wouldn't see them with the coupled dipoles. And since we're really looking sometimes at the modification of the optical Bloch equation, this coupled dipole approach is not sufficient. You should go, I think, at least to the a bit the next step, which is to keep these pair correlations, which I think it's called the mean field order 2, which is just the next order of this.
Okay, thank you.
Thank you for the nice talk. I would like to ask you about the exponential decay.
Yeah.
Because it seems like when you have dense cloud, the exponential decay actually is slower than the less dense cloud after some 300 nanoseconds.
So you mean in the long time?
Especially like from 300 to somewhere like 500 nanoseconds. Is it just this measurement, or is it something systematical?
So we kind of hope it would be even slower than that, because we know that we can populate both subradian states and subradian states. So if it was really significantly slower with a bit of more striking effect than what you see here, we could say that like we have both effects. So this could be one of the things that it's. But here the effect is very dim. We're really in the in very noisy and very dim.
Okay, thank you. And if I may, I wanted to ask about the optical pumping as well.
Okay.
So you show the optical pumping without the effect of the dipole trap. So what is your scheme experimentally here? Because I would expect the AC Stark shifts to be much stronger than the Zeeman shifts, especially in the excited state.
This is so I am not sure I understood your question, but usually first we optically pump, then we apply the magnetic field, or sometimes we apply the magnetic field and we pump with the magnetic field on, which is actually the scheme because you have the Zeeman effect, and then after we drive the atoms to the excited states. So this is the sequence.
Yeah, but the atoms should be trapped at that time, no?
Yeah. They're still trapped, but it's quite. It should be small, the shift, and
This is a perfect topic for the coffee break.
Okay.
So thank you, the
No,
speaker,
yes.
again.